All right, guys, I'm doing a general rundown for the heat in food experiment. So here's the general rundown. It'd be a really quick experiment, but a really cool one. So we would take a pre-weighed aluminum can. Okay, so we'd have this pre-weighed. And we'd fill it with a known amount of water. And on a paper clip, okay, we'd bend the paper clip somehow, some way, like so, and stick it in a cork. And in our paper clip would be a food sample, a Dorito. In my example that I'm giving my lab guys, we burn a Dorito, but we would have a Dorito or some sort of food sample. And we'd light it on fire. And what would happen is the fire would heat the can and the water. So the water's Q would be a positive and the Dorito would be a negative Q. And our goal is to see if the calories on the back of the bag of Doritos or whatever the food sample is, I'm going to keep saying Doritos, because that's the food sample I'm using, is if we can measure the amount of heat that's being released to those calories. Okay, so there's a couple things different here than what we talked about in lecture. The one big thing is, for all the stuff we talked about in lecture, the container's heat capacity was negligible, or it was an insulated container. Well, an aluminum can isn't. So what we have to take into account is not only is the water going to gain heat, but the can is also going to gain heat. Okay? And we would measure the temperature, the initial temperature, here's our thermometer, and see essentially what happens to the temperature of the water and can. Now, we're going to assume, all right, our first assumption for our intents and purposes here, we're going to assume that the can and the water are reaching equilibrium. So their initial temperature is the same and their final temperature is the same. The water and the can's initial and final temperature is the same. So if we were writing a Q expression for this experiment, it'd be the negative Q of the food, because the food's going to lose energy, is equal to the Q that the water gains plus the Q of the can. Okay. Now the Q of the food is what we're trying to calculate. We're trying to calculate this, and we're going to calculate it in joules because that is what our specific heat of water in the can is. So if I were to break down this part, and I'm going to do that right here. Okay, so we're trying to calculate this, we need these parts. The Q of the water is going to be the mass of the water plus the specific heat of water, the C of H2O, I'm going to use H2O here, and then TF minus TI, okay, so we're using Q equals MC delta T, plus the mass of the can, okay, times the C of aluminum, because we're going to assume that the can is 100% aluminum, just for our thing, and then times TF, I'll put a little multiplication of TF minus TI. So you'd have to be given information. So let's say the can will make up stuff here. All right, the can initially started at 20 degrees Celsius. And after we burned our food sample, whatever it is, all right, it ended up at 100 degrees Celsius. All right. The C of water is 4.184 joules gram degree Celsius. The C of aluminum is 0.9 joules grams degree Celsius. Okay, we'd also have to know how much water. Now, you would measure 100 mils of water out. That's roughly 100 grams. We can use the density and all that fun stuff to be more exact, but for our intents and purposes, the mass of the water is, let's say, 100 grams. Okay, and then you would have weighed the aluminum can empty, and aluminum cans are roughly 15 grams for an aluminum can. Okay, we have all the information to calculate the Q of the food. We just have to plug it all in here. So the mass of the water, 100 grams. The C of the water, 4.184 joule gram degrees centigrade. So grams are going to cancel out. Our TF is 100 degrees Celsius. Our TI is 20. Okay, so the degrees Celsius is going to cancel out. And over here, we're going to add, so we're going to take these and put this in a bracket, and we're going to add it to the can. The mass of the can is 15 grams. The C is 0.9. And TF and TI, like I said, for our intents and purposes, we're going to assume that everything gets to equilibrium, and the can's final and initial temperature, or the waters for that matter, is the same as the cans, because we would be measuring the waters. If you were doing this in a lab, you wouldn't let the thermometer touch the can. We wanted to take the temperature of the water. If we were doing this in the food industry to see how many calories a food sample has, we use something known as a bomb calorimeter, and that has a known heat capacity, and we wouldn't have to measure the can and everything like that. We would just put it in there and light it on fire, and that's what they do at the FDA to measure food samples, to make sure if you're saying it's 100 degrees Celsius, or 100 degrees Celsius, 100 calories per sample, they're making sure that you could say that, and they're testing it. So TF minus TI, 100 minus 20. So if I were to do the math here, okay, I'd have 100 times 4.184 times 80. That is 33,472 plus 15 times 0.9 times 80 is 1,000. So the can is going to get 1,080 joules. So these are both joules, J and J. And then add the two together, and I get a total joules of 34,552. Okay, and that would be equal to how much the food lost. That would equal our, and that's joules, our Q of our food. Okay, so that's step one from the data that you have, figuring out how many joules of energy is lost by the food based on your experiment. All right, so I'm going to write that number up here. All right, so here's our experimental joule value for the food. Joules, so Q of food, and that's from our experiment. Now, I want to compare it to the real life value. Okay, what should it be? Well, there's a couple things we have to take into account. When we look at our food, we don't measure it in joules. Okay, we measure it in calories, and we measure it in capital C calories. Okay, so first things first, a capital C calorie, okay, one capital C calorie is 1,000 lowercase c calories. One lowercase c calorie is 4.184 joules. Okay. So there are two things we have to take into account. All right. So what we would do is this. We'd have to weigh our food sample. All right, before we even burned it in our other data that we got at the beginning with the mass of the can and after lighting it on fire, all that other data, we'd have to weigh our food sample. So let's say our food sample weighs 4 grams. Okay. Now, if we look on the back of a bag of whatever it is or the container where our food came from, there's a serving size. Tells you, like on chips, about 10 chips have this many grams. So there's a serving size, And there's also the calories. So let's say our serving size is about 30 grams and our calories are 2,000 capital C nutritional calories. Okay. Well, we could figure out how many calories our food sample should have if it is a 4-gram sample. Okay, so now we're going to figure out our theoretical calories. We already have our experimental energy, except it's in joules. We're just going to have to do a conversion. But let's figure out our theoretical calories. There's 200 capital C calories, which I'm going to turn actually right away. I'm going to turn it into lowercase. I'm going to turn it into lowercase C calories and make it 200,000. Okay, I'm going to make it lowercase just for our intents and purposes, because we're going to have to convert that to lowercase c calories anyway. So 200,000 lowercase c, and all I did was take 1 calorie, 1,000, move the decimal 3 to the right, and over 30 grams is equal to, I don't know how many calories my sample should have, but I know I have 4 grams. So we set up a little proportion here, and we figure out our theoretical calories. Okay, so our theoretical calories will be, we're going to cross multiply 4 times the 200,000, which will be 800,000, divided by 30 grams, and we should have 26,667, give or take. Okay, so our theoretical calories for our sample should be 26,667 lowercase c calories. Now again, I'm making data up here as we go, so we'll see how it works out. Okay. So this is our theoretical calories. If we burned it in lab, what should we have gotten? Okay, this is what we should have gotten. So this is our experimental value in joules. And here is our theoretical value down here. So I'm just going to put copy that and put our theoretical value is 26,667 calories. All right, we're almost there to see how well we did in our experiment. All right, so I'm in joules. I got to convert to calories here. 34,522 joules experimentally. There's 4.184 joules for every 1 lowercase c calorie. All right, we're going to be off, but it's okay. 34,522 divided by 4.184 equals 8,000. So we got in lab that our food sample was 8,251 lowercase c calories. Okay, so this is our experimental calories. As you can see, we're way off. We're off by 3 times the amount. Now that's okay because, again, I made up the data, but this actually happens sometimes in the lab, and here's why. We're not in a closed system. We would do this in the fume hood. Number 1, sometimes the food sample doesn't completely burn. Number 2, all right, if we go back to our picture, okay, here's our can with our water and here's our food. The heat's not only going to travel this way, all right? The heat's also going to, and the heat does rise, but we're going to lose some down here. We're going to lose some out the sides. We got to take into effect we're not in a closed system. We're making up a bomb calorimeter. We're trying to get as close to the aluminum can as possible, but we're not in a closed system like an actual bomb calorimeter. So that's an experimental error. If we wanted to figure out our percent error, we take our theoretical minus our experimental, and we take the absolute value of that, even though it's still going to be positive the way we have it set up, over our theoretical times 100. So in our case, it would be our theoretical, the 26,667 minus the 8,251 over the the 26,667 and multiply that by 100. So, let me open this up here. 26,667 minus 8,251 equals that. Divided by 26,667 times 100. And I'm getting that we got a 69.06% error. Okay. So that shows you how to get your experimental value of joules. It shows you how to figure out your theoretical value of calories. We show how to get your joules to calories, and then we show you how to do percent error. It's a data sheet, guys. It'll be up online if Miss Jacobs didn't already, and I'll have my info up tonight. So it'll be on Blackboard, and mine will be due the following week. Okay, so if you have any questions, feel free to reach out to me or to Miss Jacobs. And good luck on our last lab here.